Today we are going to wrap up, well actually no, I don't think we'll get all the way through. We have to spill over a little bit till Monday. Chemical reaction equilibrium, so we got a little bit here, so I don't think we can finish it all. This here is my recommended textbook for statistical mechanics, which is what we will be starting on Monday. Now, just like with the classical, I try and make it so everything in the notes is pretty much self-contained, and if you need additional information, I'm always happy to point you in the right direction. With statistical mechanics and statistical thermodynamics, it'll be similar, where I will make sure that most everything that I'm asking of you will be something we cover in class. But this book will be useful for personal study in terms of this is something that you've never seen before. So if no one's ever seen StatMech, it may be a good idea to pick this up or to find a similar one. Now the problem you'll run into with statistical mechanics is that there's two classes of textbooks. Thin, expensive ones and big and confusing ones. Those are all you get, right? So if you rely on a statistical mechanics book like that you might have seen on professor shelves like by Macquarie or Chandler, those ones are really accessible because they've been around for like 30, 40 years, but they are not particularly useful, I would say, for learning it. If you're a physicist who looks at an equation and goes, oh yeah, of course, then maybe those books are for you, but for me as an engineer, that is the only book that I feel like that is enabled to actually teach me StatMech. Now there's one other book that I will recommend, and it's a relatively new one by Scott Shell. I had considered switching over to that book for this class, but every time I go through it, it intermixes StatMech and classical thermo, but it does it in such a way that I feel like you need to have a little bit of knowledge of both disciplines before it makes sense. So for like looking through it after you know everything, it's kind of nice how it's intertwined. So I kind of like the classical first and then the statistical second, so that's the only reason why I haven't adopted it. But if you use it as a statistical text, it's very, very good. It's really simple, breaks it down nice and well. So I can put those links up on the Canvas page as well. But that's the one I recommend. It actually does, I think, a really good job of describing what's going on. And all the complex math that's going to be a little bit more foreign, it breaks it down really, 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 really smallly. So it goes through step by step. So it doesn't say, one can show, and then gives a really complicated result. It actually does break it down, which is nice. Okay, so let's continue on with chemical reaction equilibrium. So what we need to do right now, what we first talked about, and basically the general overview was chemical reaction notation, is what we started on earlier in the week. So I'll just review that very quickly. So the number of moles of species I in a reacting system is going to be equal to how much moles are fed to the system in a continuous reactor, or how many moles are initially in the system for a batch reactor. Then you're going to have a modification based on its stoichiometric coefficient multiplied by some new parameter that we defined called the extent of reaction. Now those of you who are chemical engineers, hopefully none of this should be new information. The extent of reaction is something that we learned as freshman or sophomore in chemical engineering. So in this case, if we have some arbitrary reaction, the stoichiometric coefficient for reacting species A is going to be minus A. The stoichiometric coefficient for B is going to be minus coefficient B. For C, it's going to be positive, and D is going to be positive. So the stoichiometric coefficient for I is greater than 0 for the products, and it is less than 0 for the reactants. And this allows us to have a consistent nomenclature system such that it doesn't matter how we draw our reactions. Because in a complex multiple reaction system, which is the whole point of doing all of this anyway, we're not necessarily going to know which reaction is going to be moving forward or backwards. So having that clear consistency is really important. But just with like, do we say heat is positive going into or out of the system, or work is positive going into or out of the system, ultimately doesn't matter. As long as you're consistent, you could live your entire career switching this convention, and it's fine. But your coworkers will probably be unhappy with you. Okay. So what we need is equilibrium. Reacting systems are no different. All of the formulations of thermodynamics that we have done so far are completely generalizable, which means that equilibrium is obtained when the rate of change of Gibbs free energy is equal to 0, and in fact this is when it's at a minimum. So that would be, in the case here, what we're effectively looking to do is, if we had some plot of the total Gibbs free energy of the system as a function of our extent of reaction, we would be looking for this point right here, where dg dx is going to be equal to 0. So in this case here, dg, the extent of reaction, at constant temperature and pressure is going to be equal to 0. That is going to be our equilibrium criteria. So how we are going to integrate these two together is we're going to use this notation, combine it into an expression for the Gibbs free energy, take the partial derivative, and see what we get out of it. Everyone's clear on the procedure. So this here is exactly the same thing, right? Thermodynamics, without any assumptions, told us that when the Gibbs free energy is at a minimum, that means we're at equilibrium. We didn't have to make the assumption whether or not we're having reactions or not. And indeed, this is going to be the case whether or not we have electronic processes, nuclear processes, reactions, non-reactions, phase changes, not phase changes, right? Thermo is completely generalizable. So the total Gibbs free energy of the system is going to be equal to the number of moles of species I multiplied by its partial Gibbs, which is a function of temperature, pressure, and composition. We're just exploiting the definition of the partial molar property, right? And in the case of Gibbs at constant temperature and pressure, partial molar Gibbs is the chemical potential. So we substitute in here our expression for the number of moles of species I as a function of the extent of reaction. We will want to take the partial derivative of this expression here. Default assumption with thermodynamics. Everything is a function of everything. Let's go back and just double check really quickly. Is the number of moles of species I initially in the system a function of the extent of reaction? No, that's not. Is the partial Gibbs a function of the extent of reaction for species I? So let's say this is a two-component system. It would be partial Gibbs of A, partial Gibbs of B. If it's three components, partial Gibbs of C. Is that a function of the extent of reaction?
Yes.
Yes, because partial Gibbs is a function of the composition. So if my reaction goes either to the left or to the right, the total composition of the system changes. Right? Thermodynamics is only concerned with the end state. So the partial Gibbs, it doesn't matter if species D, for example, and C were formed by a reaction occurring, or whether or not someone just added more C and D into the reaction mixture, right? The partial Gibbs is just going to be a function of what's the molar composition of the system. Stoichiometric coefficient, is that a function of the extent of reaction? No, that is only going to be a function of the chemical reactions that we believe are occurring. Is the extent of reaction a function of extent of reaction?
Yes.
Yes, so here we go. Right? So when we take the partial derivative here, we're going to have to do a product rule here, but this one is going to go away relatively straightforward. Okay, so I will copy from my notes to make sure that I do not mess this up. Now what I'm gonna do is I'll combine these two terms here because they have a shared common variable. And you'll notice that the number of moles of species I initially plus the stoichiometric coefficient times by the extent of reaction is exactly this expression here. So that allows me to rewrite this then as the summation of the number of moles of species I multiplied by partial Gibbs, derivative with respect to extent of reaction. And this is where I regret not spending more time on the Gibbs-Duhem equation, because it's like a secret thermodynamic trick that just comes out of nowhere. This is exactly the Gibbs-Duhem equation. So the total number of moles, or the mole fraction, multiplied by the partial molar property, summed up over all species, is exactly the definition of the generalized Gibbs-Duhem equation. So if we didn't have it, we couldn't solve this. That's why it's like sort of this secret force of good in thermodynamics that saves our butts every chance we get. So that means our equilibrium criteria is simple now. So at equilibrium, the summation of the stoichiometric coefficients multiplied by their partial molar Gibbs is equal to 0. If we satisfy this criteria, that means that the Gibbs free energy is at a minimum here. Right, we just took this function here exactly. Same thing holds true for multiple reactions. So if we have multiple reactions, we have the stoichiometric coefficient of species I in reaction J multiplied by the partial Gibbs of that species I in the total reacting system. So just as a quick example of how we should want to organize our thoughts when we start to do chemical reaction equilibrium problems. So let's say, for example, we have a reacting system So we have two chemical reactions. One is the partial combustion of methane to make carbon monoxide, and the second one here is what they call the water gas shift reaction. This is the way that most all hydrogen is produced commercially. And this is also the reason why hydrogen cars never really took off, because we still got to combust methane to make hydrogen anyway in the first place. All right, let's balance this first reaction. What's our starting point? Carbon. All right, so let's just start off with one methane, which means you've got one CO. What's the next one to balance? How many should I put here? Three. And how many oxygens or how many waters do I need? Do I need to change anything else? Looks pretty good. Let's check, is this reaction balanced here? So we'll do the same procedure. Carbons look pretty good. Hydrogens look pretty good. Oxygens look pretty good. Oh, that's pretty easy. So if we were to build up a little table here, we can have species I, so we have methane, we have water, we have carbon monoxide, we have hydrogen, and we have carbon dioxide. And then we have reactions going down here. So I'm going to call this reaction 1, let's say. I'll call this reaction 2. And so in reaction 1 and 2, we can write out our stoichiometric coefficient. So for methane, it's -1. For water, it's -1. For carbon monoxide, it's +1. For hydrogen, it's +3. For CO2, there is no CO2 there. No methane, it's -1 carbon monoxide, in this case is -1, hydrogen is 1, CO2 is 1. Now if we were to write out the equilibrium criteria, in this case here, the summation of the stoichiometric coefficients, in this case here, for all the species I for reacting system 1, this equation here is going to be the same, but in this case it's for reaction 2. But we'll notice there's a connection. We need the partial Gibbs of all species I in both equations. Now, each of these are going to be a function of temperature, pressure, and the total composition. So it doesn't care how many reactions you have. So if I'm going to go about and solve this, what I need to do is I need to figure out at what extent of reaction, in which case we're going to have extent of reaction 1 and extent of reaction 2 being our primary independent variables for this system. So if I were to change extent of reaction 1, what I would be doing is I would be removing some of my methane and some of my water, and I would be creating carbon monoxide and hydrogen. But at that time, I would be changing the concentration of hydrogen, which means I would be altering the equilibrium of reaction 2. So what that means is that I have to solve these at the same exact time. So the more reaction systems that you're modeling, the more equations you're going to have. So for every single reaction, you're going to have one extent of reaction, and for every single reaction, you're going to have one chemical reaction equilibrium relationship. Now let's say we are trying to model a reactive distillation process. Then we would also have to do a vapor-liquid equilibrium simultaneously to the chemical reaction equilibrium. In which case, for every single species, 1, 2, 3, 4, 5 species, we would have to have a vapor-liquid equilibrium relationship. Raoult's law for methane, Raoult's law for water, Raoult's law for CO, Raoult's law for hydrogen, Raoult's law for CO2. Now for this case here, it doesn't make a lot of sense for Raoult's law because all these are gases except for water. But if you had a more, I don't know, realistic system for reactive distillation, that's one approach that you could take. So for a real complicated, modern unit operation process that's doing something complicated by having reactions and separations happening at the same time, there's no pretty way to handle it. You basically just have a massive system of nonlinear equations. And so then the challenge there is how do you actually give the system a good enough initial guess that it can actually grind away and give you that right answer. Any questions on this so far? Now, with this all being said, this is not actually how we're going to solve problems. Because directly calculating the partial Gibbs without approximation is non-trivial, save for if we have a really good equation of state. So with an equation of state, we can actually solve reacting systems as well. Because what's happening here is that in essence, methane, water, carbon monoxide, hydrogen, CO2, what we're doing, because thermodynamics is all path independent, hydrogen is going to be a gas, water is going to be a gas. What we're doing is we're just basically taking all the molecular building blocks and breaking them apart into their individual molecular species and then reassembling how we see fit. Now, we don't care how long this reaction takes, but what we do know is that the equilibrium will be established when this relationship is satisfied. So that still means that we can use an equation of state, which typically is not thought of as being used for reacting systems. We can use it to solve reacting systems because at the end of the day, we don't care how those molecules are made. We just know that they want to be there. Okay, so, but this system here is complicated because this function is very difficult to calculate, and even when we've done all of our phase equilibrium, we have more or less found ways to approximate it. Right? Raoult's law, modified Raoult's law, generalized fugacity coefficients, activity coefficients. right? It's just too difficult to predict it accurately for a real system. So we rely on experimental measurements, and that's exactly what we're going to do for how we typically approach it. But if we had a means to calculate the partial molar Gibbs, we could use just this setup right here, and we could do all of our equilibrium calculations. So, what we can write then, I'll just actually a little bit more talking about this here. So if we can write our Gibbs, partial Gibbs, as Gibbs of the pure species plus a correction factor from the fugacity. Right, we'll substitute this expression into here. We'll do a little bit of rearranging. Let's see, I'll skip one step. So what I've done here is I substituted this into here. I moved the pure species Gibbs to the other side of the equation. And then this logarithm stuff, I just kind of manipulated it using log properties. Does everyone follow the math there so we don't have to go through step by step? And then the final way that we typically see chemical reaction equilibrium systems being written is this one here, where we just take the exponent of both sides. It's the product sum over all of the components. Now, so just in case, so we're clear here, this is the product summation. So instead of adding everything together, we multiply everything together. But if you have a negative stoichiometric coefficient, that's like dividing. Just so everyone's clear on the product summation notation. So we can write, and these are on the equation sheet, the partial fugacity, we can write it as the as a function of the partial fugacity coefficient. We can also write this then as the pure species fugacity coefficient. So we can write this a different way. One last simplification. If this is an ideal gas, then the fugacity coefficient is equal to 1. The partial fugacity coefficient is also equal to 1. And then this gets us to our form that we should be familiar with. In the final step. The product summation of the mole fractions gives us access to what the chemical equilibrium is. So this here, let me just write this here. This is for ideal gas, and we can also write this for liquids as Right, we're just getting into now how we're modeling a particular system. So, this is the Gibbs free energy of the pure species. As a function of the fugacities in the mixture, we can substitute in approximations here for the gas phase using fugacity coefficients and partial fugacity coefficients. For an ideal gas, that simplifies just down to the gas phase mole fraction. For a liquid, it's going to be a function of the liquid mole fraction and the activity coefficient. For an ideal liquid mixture, it's only going to be a function of the liquid mole fractions. A bunch of different ways to approximate this. Now, the complication, however, of using this approach here is that the Gibbs free energy of the pure species, this is going to be a function of the temperature and pressure. The partial fugacity coefficients, these are going to be a function of temperature, pressure, and composition. So we have a lot of functional dependencies here. If I change temperature and pressure, I'm both changing my left-hand side and my right-hand side. So the convention that we've adopted is to do a little bit of a trick that allows us to simplify the approach. So again, you can use all of this if you have a good equation of state method. If you've got a good activity coefficient model, this is something that you can totally do. But the standard approach that we teach is a little bit modified from this one here. So what we do is we define a new function, a new variable, let's say. We call this the standard state Gibbs. So it is G over bar I naught. Now just keep in mind, this is not a reference state, this is a standard state. So this is a state that we agree upon has a certain property. This is going to be a function of temperature, but it is going to be at a fixed pressure of 1 bar of atmosphere, and it is going to be at a composition of the pure species. We call this the standard state Gibbs. In the case of the reference states, when we were measuring chemical reactions, we also fixed the temperature. Right, so that's what made that one the reference state for chemical reactions. In this one here, we call this the standard state. So what we do is we basically rewrite our partial Gibbs, which is a function of temperature, pressure, and composition. And we basically just add and subtract this little silly function here. So instead of substituting this definition for the Gibbs free energy, we're going to substitute in this definition for the Gibbs free energy. So what we'll write then is almost identical equation to what you saw on the first exam. So we're basically starting at the standard state Gibbs, and we're calculating how the fugacity changes, going from the standard state to the real state, which gives us the real Gibbs. We're going to define a new function now. This here, does anyone know what this is called? And remember their undergraduate reaction engineering. It's called the activity. Getting really into the weeds right now. This is where my expression where I say thermo is the system, this is where we're like, chemical reaction equilibrium is like the system. You have to follow the system, otherwise it makes your life a lot harder. So, what we're going to write then is that the Gibbs, partial Gibbs, is going to be equal to the Gibbs at the standard state corrected by its activity, which is the ratio of the partial fugacities. So in this case here, activity is defined as the ratio of the partial fugacity in a real mixture from the partial fugacity at the standard state. In many ways, this is just funny, clever math. So what we'll do is reformulate everything that we've done. The reasoning behind this now, though, is that the Gibbs at the standard state is only a function of temperature. The partial Gibbs here, we're going to substitute this into. All right, so we're going to get rid of the left-hand side. The activity is now going to be primarily a function of pressure and composition. All the temperature changes that go on in our system are going to be lumped into our standard state, which means that transitioning from our standard state at a constant temperature to the real state at a constant temperature, that means that the partial fugacity only needs to vary the pressure and the composition. So what this is allowing us to do is to take one expression where both sides depend on all variables and break it down to where one side just depends on pressure and composition, the other side only depends on temperature. So if we do exactly the same approach right here, where we write that the summation of the partial Gibbs multiplied by their stoichiometric coefficients is equal to 0 at equilibrium, we substitute in our expression here. So exactly the same procedure, but in this time here, what we're going to be getting is an expression that looks like this. This is our master equation for chemical reaction equilibrium using sort of the most convenient agreed upon conventions. Sorry. Yeah, that's right. So the only other approximation that I've done is that the summation of the stoichiometric coefficients multiplied by the Gibbs, that's just the Gibbs of the reaction. So that's what this simplification is here. These two terms here, that's the delta G of reaction. It's the same definition. This is the equilibrium constant for the reaction. Now, oftentimes you'll see this written as exp of minus delta G of reaction over RT. So, if my equilibrium constant is greater than 1, does that mean that my delta G is positive or negative? So let's see, delta G 0. So if my Ka is greater than 1, that means my delta G is negative, meaning that I have a large driving force to go forward in the reacting process. If my Gibbs free energy is greater than 0, that means that I have a desire to push things back. So what I have here, I'll pass it out. This is another big table in the Sandler book that has approximations for the activity. Whether or not you want to assume it's a highly pressurized liquid system, a low pressure liquid system, an ideal mixed liquid system, a non-ideal liquid mixed system, an ideal gas system, or a real gas system. There is your Bible for all the different permutations of that approach. One other quick note here, let's see. It's just a few more definitions. Just to be clear, so the delta G of reaction at the standard state is just the summation of the stoichiometric coefficients. And we have temperature variations in the equilibrium constant. So this is something that I really haven't talked about too much in class, but in general, looking at changes in free energy, they're going to be related to the changes in enthalpy as a function of temperature. It's the same thing with actually activity coefficients. And then lastly, if we can assume that the heat of reaction is constant, so if delta H of reaction is not a function of temperature, we can partially integrate this expression. Okay. I believe that kind of wraps it up. Well, if the delta H is a function of the heat of reaction, that means that the delta H of reaction is going to be depending on the heat capacities of the individual species. The Sandler book has a nice equation that is really unpleasant and very long, but really easy to understand, where you basically add up all of the coefficients of all the heat capacities for the products and the reagents. So if we take an arbitrary chemical reaction, let's just say okay, so let's say we do an arbitrary reaction here. I want to know what's my heat of reaction as a function of temperature. As I heat up this system, right, thermodynamics is path independent. So it doesn't matter if I could perform this reaction, let's say at T equals 25 degrees C, which means we're at the standard state and the reference state. Or sorry, the reference state, sorry. So I can calculate the heat of reaction using, the heat of formations, right? That's what we talked about on Wednesday. But then if we need to come up with what's the delta H of reaction at, let's say, 500 degrees Celsius, what we can do is we can take our reagents, cool them from 500 down to 25, then we can react them at the reference state, where we know with the heat of reaction is at 25 degrees. And then we heat them up again, 500. But the difference is going to be that the heat capacity is not going to be equal when you have the products versus the reagents. So the imbalance in the number of moles and the heat capacities of those individual species influences how the heat of reaction changes as a function of temperature. But when we do these calculations, right, just exactly as how we did delta H and delta S calculations with the equation of state, we always went to the ideal gas state, did everything in the ideal gas state, and then went back to the real fluid. With reactions, we're going to be doing almost the same approach, but instead of going to an ideal gas state, we're going to take it to the standard state, or the reference state. Is this familiar to a lot of people? So hopefully this should all look not new if you're coming in from a chemical reaction background, or even a chemistry background, you should see similar stuff. Okay, so let's now simplify our expression here. Let's see, do I have time to go over, let's see, maybe I have time to go over an example. So let's do one quick thing. I just want to quickly write for an ideal gas. Can someone tell me what is the activity for an ideal gas? At least from the sheet there. How do we write activity? So A sub I is equal to what?
An ideal gas the same as a pure gas.
I think so. In the table here. Gaseous species in a liquid mixture. So that would be species in a pure gas mixture. So I guess they don't have ideal gas on here. But we're going to be dealing with a gas mixture. So how do I write my activity then? So we have the partial fugacity of species I in the vapor over the fugacity of species I at temperature unknown, pressure of 1 bar. So for an ideal gas, so for a real gas, if we follow this chart over here, we can write this as, oh, here we go. There's simplification for low and moderate pressures on the edge. So P divided by 1 R. So in the case, same thing in the case of Raoult's law, the partial fugacity of species I in the vapor phase, we approximate it using the Lewis-Randall rule, where it's just the mole fraction multiplied by the pressure. The fugacity of a pure low pressure gas, in this case 1 bar, is just going to be equal to, in this case, 1 bar. So the tricky thing with activity is that if you're doing a reaction at a pressure that's not 1 bar, you have to make sure that you always do your pressures in units of bar. Otherwise, it's not going to work out. All right, so we take a look here. We'll have an equilibrium constant. This is easier to write than this big mess right here. Is going to be equal to the product summation of, in this case here, it's going to be YIP over 1 bar raised to the stoichiometric coefficient power. Right, this is our activity. Trying to rush through, because if we can knock this out, then I don't think we have to do too much on Monday. So this is going to be our equilibrium expression. Let's say we have access to the Gibbs free energy change of the reaction, which means we can calculate the equilibrium constant for this process. What I'd like to do now, really briefly, we can go over it again. We'll probably have to do this again, but let's say we have an arbitrary reaction. Let's say 2A plus B going to 3C plus D. Again, this is the system that we use to kind of help us solve this. So we want to write this expression for that reaction. So So what we'll want to do is first take note of the stoichiometric coefficients. So in this case, it's going to be the mole fractions. So the numerator is going to be the products because they have positive mole fractions, which is going to be the numerator. So it's going to be the mole fraction of species C multiplied by the system pressure divided by 1 bar raised to the power 3, mole fraction of species D multiplied by the system pressure over 1 raised to the power 1 divided by the mole fraction of species A times by the system pressure divided by 1 bar raised to the power 2, mole fraction of species B times by the system pressure over 1 bar raised to the power 1. So then we can rewrite this looking at just the mole fractions, y of C cubed, y of D over y of B, multiplied by all the pressures. So we have 1, 2, 3, 4 pressures on the top, 3 pressures on the bottom, so we're left with an imbalance of P over 1 bar raised to the power of 1. Now the one thing that we don't have time to do is an example. All we need to do now is find a way to rewrite the mole fractions of the reacting species as a function of the extensive reaction. And then we have one equation, one unknown, and we can solve our chemical reaction equilibrium system. So we'll have to go over how to do this, or sort of the standard convention of how we do this on Monday, and then hopefully we'll have a chance to start StatMech on Monday. Any questions? All right. Well, good luck in finishing up the homework, everyone. 5 o'clock is hopefully when I have it set due. That's what I intended it for. And see you on Monday.